Okay, guys, we are working in chapter 3.8. This is about exponential growth and decay, and we're going to be using a natural model. That is the base E model. This is what it looks like. P of t equals P naught times E to the kt, where P naught is the initial amount and where K is referred to as the growth or decay constant. If K is positive, it's a growth problem. If K is negative, it's a decay problem. So these are, of course, involving the derivatives of the base E function. And of course, this is going to involve the inner chain rule as well. So in general, the derivative P prime of t, I'll put that right here, is equal to K times P naught times E to the kt. Again, because this is a inside chain rule, so the derivative of kt is equal to K. So there's your model for growth or decay, and there's your derivative in general. So let's take a look at an example of this then. Suppose, and we'll pick some easy numbers here, but suppose that we have a population of 100 bacteria at t equals 0 hours. So t is the time in hours in this particular problem, and P naught is equal to 100 bacteria. So we have P naught equals 100 bacteria, and we have our growth constant K is equal to 0.08. Again, I'm just picking some numbers here. So this roughly represents about an 8% growth rate per hour, since time is in hours. So our model, P of t, is going to be equal to 100 times E to the 0.08 t. This will tell us how many bacteria we have as a function of time t in hours. Now you could just plug this into your calculator in order to answer the question of how many bacteria there are, let's say after 4 hours, 5 hours, whatever, okay? But we're more interested, since this is calculus, in the question of how fast is this population growing in 4 hours or 5 hours. In order to answer the question of how fast, that's a rate of change, and so therefore we need the derivative. So therefore, P prime of t is equal to 0.08 times 100 times E to the 0.08 t. Of course, I'm going to simplify this because 100 times 0.08 is just equal to 8 E to the 0.08 t. All right, let me show you this, and then we can answer the question of, let's say, how fast this population is growing in 4 hours. Okay, so there's my derivative, simplified, of course. And all we have to do is plug that into the calculator. to be able to answer the question of how fast the population is growing. So again, let's say that I wanted to know how fast this population was growing in T equals 4 hours. So in T equals 4 hours. So I'm going to plug that into my calculator. I'm going to use, of course, the 8 times e to the 0.08 times t, which in this case is 4 hours. So I'm going to get 8 times e to the 0.08 times 4. And I get approximately that. So I like accurate answers, and I usually ask for anywhere from 2 to 4 decimal places of accuracy, depending on what we're dealing with. And so doesn't WebAssign and the textbook. So P prime of 4 is approximately equal to 11.017. And that is in bacteria per hour. That's how fast it's growing right at T equals 4 hours. All right. Now, there's one more thing that we need to look at in looking at growth, exponential growth, that is. That is a concept known as doubling time. So we have a formula for that. I'm not going to derive it. If I had a full lecture and this was a face-to-face class, I probably would, but I'm not going to. So doubling time formula, I'll call it DT, is equal to the ln of 2 divided by k. So in this case, it's the ln of 2 divided by 0.08. And so therefore, that's going to be approximately, back to the calculator, it's a natural log of 2 divided by 0.08. And that comes out to be approximately 8.664. So 8.6, approximately 8.664 hours. What does that mean? That means that in approximately 8.664 hours, there's going to be 200 bacteria. So the initial 100 has doubled to 200. Okay. So that covers an example of growth. Let's take a look at an example of decay. Same formula, same derivative. Let me erase this. Give me a moment. Okay, let's say in this example, now again, we're using the same formulas, the same model for decay as we're using for growth, P naught times e to the kt, same derivative also, obviously. So let's say that we have 50 grams. of, let's say, plutonium 14. And that, of course, is initially at T equals 0. And let's say that the time is in years. Okay, of course, the time is dictated by the problem. These are all kind of applied problems anyway, so you're going to read carefully. So the time is in years, and the decay rate, let's say that K is equal to negative 0.018. Okay. So we have 50 grams of this radioactive material at T equals 0 years. That's the initial amount. And the decay rate is negative 0.018. So we're going to use the same model, except that this is not a growth model, it's a decay model. We know it's a decay model because the value of K is negative, and because when we read the problem, we know that this radioactive material is decaying. So we have P of T is equal to 50, which represents the 50 grams, times E to the negative 0.018 T, where again, T is the time in years. Now, yes, the decay rate is slow for a lot of radioactive materials, but not all. And that doesn't mean that you should assume that it's definitely slower. So here's our model with our information plugged into it, okay? 50 times E to the negative 0.018 T. The question, again, would be how fast is this material decaying in, I don't know, let's say 20 years, okay? Again, the key word here is how fast, and of course that means a derivative. So we have to find P prime. So P prime of T is equal to negative 0.018 times 50 times E to the negative 0.018 T. And then I'll simplify this, which it should be. So P prime of T is equal to, use my calculator here, 50 times negative 0.018. I get negative 0.9. E to the negative 0.018 T. All right, so here's my derivative. Notice that the decay rate is going to be negative, which means, of course, it's decaying. It's losing its mass or volume because it's a radioactive decay. Well, now let's plug in T equals 50 years into this derivative. Calculators, guys. So it's negative 0.9 times E times E to the negative 0.018 times 50. And I get negative 0.366. That's accurate to 3 decimal places. So I get that P prime of 50 years, that is approximately equal to negative 0.366 grams per year. So that's how much it's losing in 50 years. So notice that the number of grams that it's actually losing in 50 years is relatively small, because it's probably lost most of its mass by then with a with that particular value of K, that is. Now, again, one thing we haven't done here is determine something called the half-life. And I don't have a lot of room on here, but I'll give you the half-life formula anyway. So we're going to erase some of this. That is, I'm going to erase the P prime of 50, which is already recorded here. All right, so let's calculate the half-life of this substance. So the formula for a half-life is equal to the ln of 1/2 divided by K. So it's obviously very similar to the doubling time formula. So in this example, it's going to be the ln of 1/2 divided by negative 0.018. Now, before I show this to you, of course, I'll punch this into my calculator to come up with an approximate value of this to accurate to a couple decimal places. So I've got the natural log of 1/2 divided by negative 0.018. So it looks like it has a half-life of 38.508. That's in years. And that would be, of course, in grams per year. All right. So that's a half-life. So these two concepts of doubling time with a growth problem and with half-life in a decay problem are also concepts that you need to know. All right, so we will stop this recording.